Hello, welcome to today's FSEG webinar, Design and Implementation of a Soil Survey Program with series speaker Benedikt Steiner. My name is Deanne Ryder. I'm the online community manager and the webinar coordinator for this series. I will cover a few logistics for the webinar and a quick overview of FSEG before I turn it over to Benedikt. If you have any problems viewing today's webinar or your screen freezes, just try to refresh your screen. Normally this can be done by clicking Control F5. And if you have any problems with the audio, you can also join by phone, but there might be some toll charges that apply, so please keep this in mind. Otherwise, you can join with computer audio by clicking the arrow next to the Join Audio button and selecting Test Speakers and Microphone. And that'll give you the call-in information or the way to test your computer audio. If you have a question, we encourage you to submit those by using the Q&A button at the bottom of your screen in the control bar. Today's call will be listen only for participants, but feel free to ask questions throughout the webinar and we will respond to those as time permits during the 3 Q&A periods that we have during today's webinar. Today's webinar is part 3 of a 4-part series targeting the needs of students and early career professionals. It is being recorded and an archive will be available following the event on the FSEG website as well as the FSEG YouTube channel. We have a playlist set up there for all of the webinars, so feel free to go back there and listen to anything that you might have missed. It normally will take about 3 to 4 business days for us to get that up, so check back. And then this is our next webinar coming up in December, and I encourage you to go ahead and register for that now. And that way you'll be in all the correspondence with details for the call. The webinar series, as I mentioned, the idea behind this was to raise awareness in economic geology and to help early careers and students find their feet in the mineral industry. We hope that this will provide essential job skills, and today Benedikt is going into more detail on the soil survey programs. Quick overview of FSEG. We're a society devoted to advancing the science, discovery, and responsible development of mineral resources. We are comprised of members all over the world with about 118 student chapters. And there's a focus on early career committees with the early career committee trying to connect students and more senior professionals. A quick plug for membership, our renewal is now open, so if you are a member, please go ahead and renew, and if you haven't joined FSEG, I invite you to do so. We have a lot of exciting things coming up in the next year. This is a quick overview of some of the highlights for FSEG members, just that they have a network that they can connect with and a mentor, and then some of our publications. But in this next year, we will be celebrating our 100th anniversary of the society. And to celebrate that, we will have a series of regional field trips. We will be creating an online community to help continue the conversations and questions from in-person events or these webinar series into the online world, so that conversation can continue. And we'll have a podcast series, and all of this will culminate into the FSEG 2020 conference in Whistler, British Columbia. And with that, I will turn it over to Benedikt for the presentation. Benedikt?
Thanks very much, Deanne. As you already alluded to, today we are going to have a more technical session on soil surveys and soil geochemistry, whilst the last 2 webinars have more focused on overall soft and technical skills. We will look today into the intrinsities of designing and actually carrying out such a program during a mineral exploration campaign. So we start off with a quick overview of what actually is exploration geochemistry. We will then take a look at soil geochemical surveys, primary and secondary dispersion. I will also emphasize the importance and necessity of orientation surveys at the very beginning of such exploration campaigns. We will also take a look at practical aspects of carrying out soil surveys and have a quick look at digest and analytical techniques that are of great importance in obtaining the most appropriate results. At the end of the webinar, I have also 2 small case studies of how such soil surveys were implemented recently, just to show you the powerful nature of this kind of survey in mineral exploration. I'm just trying to move to the next slide, sorry. So what is exploration geochemistry? I found a few years ago an interesting definition published in the ALS geochemistry newsletter. ALS is a commercial laboratory, and in this newsletter, exploration geochemistry was defined as utilizing trends and patterns in trace element distribution as indicators of concealed mineralization deep below the surface or at a great distance from the current location. Increasingly, today's explorers require lower detection limits and a wider range of elements to identify prospective targets. So clearly, this definition says that exploration geochemistry is one of the crucial tools in finding mineral deposits, particularly in areas that are experiencing either secondary transport or that dispersion, or showing a great thickness of overburden. Now we're going to take a look at how this exactly works for mineral exploration programs. But what I wanted to also emphasize is that exploration geochemistry is quite different from the, let's say, academic geochemistry that's usually been taught at universities. The key difference is that in mineral exploration and mining, usually a great amount of samples are collected on a routine basis. So, for example, it's not uncommon to collect thousands of soil samples in specific areas, and of course a company would expect that these samples are analyzed and returned within a short period of time in order to enable business decisions to be made. So if we start off with some basics, I would like to introduce you the concept of primary and secondary dispersion. These 2 images here have been taken out of an undergraduate textbook, and they are simplifying the concept of the distribution and redistribution of elements and minerals in a primary magmatic or hydrothermal system. So you can see on the left-hand side a classic magmatic fractionation sequence where you have a number of crystallization events. So in stage number 1, at high temperatures, you experience crystallization of olivines, and that's happening in ultramafic to mafic environments. And then as you decrease the temperature of the melt, you have consecutively more and more minerals being precipitated and crystallizing. And those minerals, they change from mafic to more of a felsic chemistry. So whilst you have in stage 1 usually minerals like olivine precipitating and forming, towards the end you experience usually quartz and other felsic components to form the latest stage of the magmatic crystallization cycle. And we can straight link this back to mineral deposits. In stage 1, you would see these ultramafic nickel, copper, PGE deposits, whilst towards the very end of this sequence here, you have melt enriched in incompatible elements, as they have quite large ionic radiuses and cannot be incorporated in these earlier minerals. These deposits in stage number 4 are usually forming pegmatitic or tin and tungsten related deposits. So clearly, magmatic fractionation and the the development of a magmatic melt will also have an influence on how your elements move around. If now in a magma chamber experiences structural and tectonic forces and control, you see very often magma being squeezed out of a primary magma chamber and being emplaced in dikes and other magma chambers away from the primary location. And this really forms and helps to form these late-stage magmatic deposits, such as pegmatite veins in country rock. Now, if we move ahead away from primary dispersion and we weather rocks, we weather an ore deposit, we quickly see the effects of what is called secondary dispersion. So this example here from Canada shows one of these unconformity hosted uranium deposits in Saskatchewan, and you can see that in the center of the image you have this uranium deposit sitting. It's been emplaced at the boundary between the basement and overlying sandstones. Now, through the action of basin water and water flow, you have ions and metals migrating up fractures, and these ions and metals are then accumulating in the overburden, which in Canada is often glacial till and other quaternary material. This is usually what geologists are sampling in the field. And you can see there's a little inset image on the bottom. Geologists usually collect soil, stream, or vegetation samples in order to trace signatures of such ore deposits in a superficial environment. Now, understanding the mobility of such elements is of great importance in delineating the location of a buried and covered ore deposit. And nowadays, we are experiencing exactly this kind of situation where the easy to discover ore bodies have largely been found, and we're now looking in other exotic locations or in locations that have 100 meters of glacial cover. For example, last week I've been in South America, in Guyana, looking at some greenstone-hosted gold deposits. And again, in Guyana, you will find 100 meters of tropical laterite cover. So clearly the question there was, how can we look through this cover and find gold deposits? And this really employs techniques such as geochemistry and geophysics. Moving on, soil surveys, which are the topic today, represent direct detection of anomalous elemental concentrations and mineralization through weathered residues of bedrock. In cases where you have residual soil, this might be beneficial, as immobile elements will tell you about a signature of the bedrock in the subsurface. However, in places like the Northern Hemisphere and Canada and Scandinavia, you will have the effects of quaternary movement of soils by glacial action. And this really complicates the matter considerably. So understanding element mobility, particularly in areas affected by quaternary geology, is very important. However, soil surveys are still a standard tool in regional exploration and prospect delineation. And it is one of the common tools that are usually employed in grassroots exploration. So if you have just left university, I'm very sure that one of the tasks that if you find a job that a company is asking you to do is carry out a soil survey. So I hope that you find this webinar useful and can use some of these aspects mentioned in your upcoming fieldwork season. I think that brings us to our first questionnaire. Deanne, if you could bring up that poll, please. And I just wanted to ask the audience if you have ever conducted a soil survey program before, just to get a feeling for how experienced the audience is in soil surveys. So if you make your choice here and submit, then we can take a look at what the outcomes are. Okay, Deanne, if you maybe can show the results. Yep, we have a clear winner here. So 60% have already conducted a soil survey program before, and about 40% have or are planning to do one in the near future. So that's great. So the 60% amongst us, I hope you will find some of the aspects here useful, and I hope to give the others a bit of a better insight of what is required to carry out soil surveys. Great. Let's move on to the next slide. I think, Deanne, if you could move on to the next slide, please. Yep, already a question and answer session. I have one question coming up. Let me quickly read through that. So one comment was, from my experience, soil development is largely a function of topographic position. Local highs are more rocky, while low-lying areas have thicker organics. My question is, how does this variability affect the soil survey when consistency in sampling is vital? That's an interesting question. And as you say, usually in the Nordic regions, you have the topographic highs are usually exposed with bedrock, whilst the lower areas are more swampy. Now, I'm going to talk about this actually in a few moments, where I present what's to be covered in orientation studies and finding the correct soil sampling procedure. So if it's okay, I'll just move on, and your question should be answered in one of my slides. Okay. Deanne, if we could move to the next one. Okay. So if we talk soil surveys, commonly the procedure is that you have a preliminary understanding of the ore body dimensions. So what I mean here is, if you're exploring for a porphyry copper target, you're expecting to have a large geological body with many alteration zones ranging over several kilometers. Whilst if you're looking into lode gold deposits, the elemental signature of such an ore deposit is quite narrow. So what the ideal procedure is that you cover an area which is at least 10 times the width of an exploration targets on both sides. And that is really to get an idea of the background values of in the area you're investigating. Of course, you might ask, is this a practical approach? And very often, especially if you're in overstaked geological belts, this approach might find its limitations, as you cannot secure license areas over such great distances. However, ideally you want to implement best practice and take this into consideration. Soil formation is an important aspect to consider. Soils usually form over quite a long time, and they are usually a weathering product of underlying bedrock. Okay, so soil horizons may usually differ in appearance throughout climatic zones, but the common principle is that you have a number of soil horizons developing as a result of superficial leaching, and which is also called alluviation, and then the redeposition of metals in a lower soil horizon, which is called the B horizon, zone of accumulation, or alluviation. And I'm going to show you in a few moments a photo of such a very distinct leaching profile. And that, of course, has some implications on what soil horizon to sample. Moving on to the next slide, I would like to introduce the importance of orientation studies. Now, a common mistake that people can do is to start a soil program out of the blue and not completely planning out the investigation in detail beforehand. So if you enter a new geological area or new area with differences in soil composition, it is very much advised that you carry out an orientation study in order to help you identify the key parameters that you actually need to employ in such a survey. For example, you need to study beforehand what kind of material you're actually sampling. So is it rock only that you sample? For example, in rocky deserts, you have usually quite a very thin layer of soil, or sometimes it's calcrete. And it's really important to understand what is the material, how is the soil made up of, and what minerals does it consist of. You need to determine the optimal depth or location of your sample. And as I mentioned before, because of alluviation and alluviation processes, determining whether you sample your B horizon, the zone of alluviation, or whether you sample topsoil is becoming an important task. You need to determine the size. I mean by size, the amount of material that you collect. So if you collect 500 grams or number of kilograms, and you need to determine what is the ideal grain size in your sample. You also need to investigate the sampling density and pattern. And on the right-hand side, you will find an overview of a Canadian soil sampling program that was published a number of years ago by the Geological Survey of Canada. That depends, of course, what your aim is. If, like in the case of a geological survey, you cover large areas, a regional sample density of one sample in 4 to 7 square kilometers is enough. However, if you're delineating a prospect in more detail, it is often advised to lower down your spacing of samples to 25 or 50 meters. It is also critical that you determine beforehand the different preparation, digestion, and analytical techniques. So nowadays we have got quite a variety of analytical techniques that laboratories offer us. I have a few slides about this later, but it depends on the kind of deposit you are exploring for. So there might be techniques that target mobile metal ions, and there are also other techniques targeting a full digest, a full decomposition of the rock, which may help you to understand bedrock signatures better. So really, the analytical techniques should be known beforehand, so that your sampling program can be improved. At this stage, being aware of quality control procedures is equally important. So usually during such sampling programs, you would need to insert duplicate standards and planks in order to monitor accuracy, precision, and lab contamination. And it's advisable to determine the insertion rate of such quality control samples early on in an orientation study. Having then analyzed a number of these orientation samples across one or more source sampling lines, you will be able to determine the background and anomalous values through a number of geostatistical procedures. So that helps you to actually identify what population is anomalous in your area, which may be different from area to area that you're working in. Here's an example of, on the left-hand side, of soil profile through a boreal forest soil in Finland. And you will see very clearly here that a number of soil horizons have developed. You have the so-called AH horizon, which is the humic portion of the A horizon, and then it also includes mineral matter. You've got the so-called AE horizon, which is completely leached. So alluviation has taken place here and deposited a layer almost deplete of any metal signature. That's why it forms a consistent white quartz layer. And down in the B horizon, you can see orange colors, which are typical for iron, manganese, hydroxides, clays, and other minerals that can host a mineralization signature. This test pit here was dug as part of an orientation study to determine the composition of the soil in this specific area. And by digging a number of such test pits, it becomes clear to the geologist what source sample to target using a number of analytical techniques. For example, the B horizon, or even further down, the B to C horizon, is an important sample medium if you would like to minimize the effect of glacial transport, because the closer you sample to bedrock, the less a sample has moved through glacial action. Whilst if you're interested in ionic techniques, so techniques that just basically remove ions adsorbed to mineral matter on the B horizon, you would sample about 20 to 25 centimeters in that particular pit. New techniques recently have also been tested on the AH horizon, where a number of weaker aqua regia digests were successful in delineating a number of anomalies. However, all of this should ideally be determined in an orientation study, so that by the time when you start a soil survey, you know exactly what is the best soil horizon to target and which is the best analytical technique to employ. The results of such an orientation study can be seen on the right-hand side, and I've plotted here the results of a tungsten and base metal exploration campaign that we were running a few years ago. You can see a number of these histograms here that look into, on the y-axis, the weight of grain fraction versus the different mesh sizes that were used on this survey. And you can also see on the right-hand side the concentration of copper values in gray and tungsten values in blue. Now, my question to you in the next poll is, which of these grain sizes are the most appropriate for tungsten and for delineating tungsten and copper anomalies? So if you could perhaps take half a minute or so and just digest these graphs and tell me which soil horizon or which mesh size you would use in this survey. Okay, maybe Diane can show us the results here. Great, good news. So about 42% of the audience would go for the -75 micron mesh size. And I agree with you. You can clearly see that in all of these samples that have been analyzed, the -75 micron fraction largely gives the best geochemical response for both tungsten and copper. And it's a very worthwhile exercise to do before starting your exploration campaign, as it will determine clearly where the anomalies are located, right? So if you looked into the more coarser fractions, you wouldn't get as a pronounced of a signal as you would with the -75 microns. Thank you very much. I've just had also a very quick question coming through, which fits into the sampling technique here. So the question is, in your experience, is there a better method for sample collection, shovel versus auger? In areas with a thin B horizon, it can be difficult to collect enough material to make up a sample, meaning that up to 10 auger holes need to be drilled. It's a very good question, and I've encountered that myself very often. I usually prefer to sample using a shovel, using such as the one that you see on the left-hand side on this photo. Using an auger, you have to drill many different holes around a short spacing from the actual target location. So I would definitely opt for going for shovels. You need to make sure though that these shovels are sandblasted. That means that shovels do not introduce any contamination if they have some cover on to be stain resistant. Okay, let's move on to the next slide. Sorry. What equipment do you need for soil sampling? you of course need to start off with knowing where exactly you are sampling or you're taking your samples. That is usually done in preparation study or preparation work. In GIS software, you would upload your sample locations that can easily be transferred to a GPS, or nowadays using smartphones. There have been developments in the last few years where companies like Esri or also QGIS developers have introduced so-called apps, GIS apps for smart devices and iPads. And those really mean that you can nowadays take a GIS shapefile layer into the field and directly manipulate and enter data without having to use these traditional sample paper cards. You may have experienced this yourself as well. You'd need a ruler if you determine the sample depth and you try and stay consistent. That would be helpful. You need a number of sample bags, ideally labeled and stapled with sample numbers. If you do this beforehand, you avoid losing time in the field. You need usually cable ties to make sure the sample is not disappearing from the sample bag and avoid contamination. A number of sieves are usually required to be carried around in the field. And these sieves, they can range, of course, in mesh sizes. In the previous slide, we've seen that the ideal mesh size for that particular study was -75 microns. Now, this could be quite impractical in the field, as -75 microns, so we're talking silt to clay size fraction, is actually quite time-consuming to sieve this in the field. So usually what I'm doing is I'm taking a coarser or a larger mesh into the field, such as 2 millimeters, and then either send the samples to the lab where they can be sieved down to -75 micron, or I can do this also back in the field camp, just to maximize the efficiency in the field. Apart from these hardwares here, like picks, shovels, spades, and machetes, you should also carry a first aid kit, just to make sure the health and safety is covered. But really the most important aspect here is, of course, the staffing. So usually soil sampling campaigns are carried out using large field teams, especially if you are in remote areas. It's a great idea to have a number of skilled field technicians around who have done these, who are not necessarily geologists, but can but understand what is required from the field samples. If geologists are accompanying the field teams, it's of course important that they supervise if the samples are taken appropriately. So if the correct soil depth has been sampled and that no contamination is introduced. There are a number of procedures that I can go through here. If you're in the field and you have loaded your soil sampling locations onto your GPS or mobile phone app, you would locate the sample site first. And if required, in the orientation study that a certain horizon has to be sampled, you would dig to this predetermined depth, and you need to ensure that the topsoil materials, so the organics, that you separate them from deeper materials in the process of digging out that hole. The field technician or geologist needs to then confirm whether the final depth has been reached. Again, if you have very shallow desert soils, that might be quite a problem. You would run the material through the sieve of your choice, and you want to avoid to introduce organic matter into the sample, especially if your target material is the mineral soil and not the organic components. In order to avoid contamination, it's advised that you clean the sieve equipment with a brush and a cotton cloth. Otherwise, you risk that mineralization signatures are carried from sample to sample, and so the samples are contaminated. That should be avoided. Very often, however, your samples will be wet, but an easy practical fix is to dry these samples in your field base camp, or if need be, send the samples to the lab and have them dried in large laboratory ovens. Now imagine if you collect hundreds of soil samples, and you're not rehabilitating these holes, you're leaving at times quite deep holes in the countryside, which is of course not ideal for wildlife or for other people who are living in this area. So a good idea is to be responsible and refill these holes and rehabilitate the holes so that no incidents happen. However, once you collected your soils, from my experience, the job is not yet done. There are a number of back-in-camp jobs that require the attention of the geologist. You can see here on the right-hand side in this photo an organized sample farm. And this sample farm probably consists of about 200 samples, which have been bagged and labeled and are ready to be dispatched into to the lab. So if you arrive back in camp, you should offload your samples and make sure that no sample has been lost. That can happen. I recommend to store the samples in numerical order in your sample farm and have a field assistant ensure that everything is nice and neat. You should determine which samples need drying, and I advise that these smaller sample bags, they can be put into rice sacks, we call it in Africa, and to dispatch them more easily to the lab. As a geologist, you should download the GPS sample points from the GPS and transfer them to your computer. Make sure you save them as shapefiles and plot them in GIS. That's a very good quality control tool in order to see if GPS coordinates have been recorded correctly. So if some samples plot way out of the area where you're working, you know that you have a problem with the sample data collection. The geologist will also clean these shapefiles and data sheets from errors, and you would also upload the new locations for the following day. What I recommend is that field teams carry out and produce such timesheets like you see on the bottom of the slide. That really helps to keep track on what the productivity of the sampling teams are throughout the field season. So you can see that during a period of about 2 weeks, about 500 or 550 samples have been collected by just about 2 geologists. In this type of African terrain where it was sampled, that was pretty good going. And that, of course, helps to produce your weekly reports that you send on to management. It's a nice and easy tool to keep everyone updated. As you can imagine, doing all of this during the day your job is not finished after about 8 hours. But this is definitely not a 9-to-5 job. So by the end of the day, when you're finished with all of these exercises and tasks, I guess you should not forget to call home, call your family and friends, because these days can be quite exhausting, especially if you carry out such a task over several weeks or months. Good, so that leads us to the second Q&A session. I see that a number of questions are coming through. Let me quickly look through them and answer them. Is there value in doing a soil survey in brownfield exploration? And yes, indeed, I think it's very common usually to do soil surveys in brownfield exploration. It really depends what stage your project is in. If you mean by brownfield exploration that resource is delineated for the mine site to just continue mine operations, then probably drilling will be the straightforward tool. However, if you're having a large mining lease, you would, and you haven't explored this in great detail, you would need these techniques as well. So I can confirm that a soil survey in brownfield exploration is commonly needed. Another question here is, are calico bags also okay for collecting soil samples? Would it cause contamination? I think calico bags are definitely doable in the field. Calico bags, for those who don't know, are heavy cotton bags which allow water to drain out. So if you have, for example, a moist or a wet sample, that would mean that some of the moisture disappears. It can be actually quite beneficial to dry out your samples in such bags. However, I appreciate your concern if that introduces contamination. In this case, I usually use 2 calico bags for the same sample, so that if anything would be escaping, it would be captured in or collected in the second sample bag. Here's another question that I quickly answer. And the question is, some governmental surveys, such as the Canadian survey, collect a lot of metadata with their source samples, such as multiple site pictures, color, texture, percentage of silt clay, slope, vegetation time. This can take a lot of time at each survey site. Do you think that in the industry environment, this kind of metadata is necessary and beneficial? I have a very clear answer to this. Yes, such metadata is definitely necessary and beneficial, because these data later on, they will help you to identify if there are any issues with your sample. So, for example, if a sample later on is analyzed and contains anomalous values, then you would like to have as much information as possible available to you to make a decision and a final explanation for why the sample is anomalous. However, nowadays, as I mentioned before, with the introduction of these smartphone apps, this capturing of the metadata can be quite quick. Okay, so if you set up this app in a way that you have only a number of different options to choose from, then that'll take less than 5 minutes. I've done that several times over the last few years, and it really helped me to fast track sample collection in the field. These smartphone apps also allow you to capture photos, so it's not a big deal in including photos in a database. I hope that answered the question sufficiently. Okay, so I think we should move on to the next few slides. Deanne, if you could kindly move to the next slide. Yeah. I wanted to give you also a quick heads up on analytical techniques, as this seems to be a common issue with sample collection and sampling surveys. If you look into the service schedule of commercial laboratories, you will find dozens of pages of different digests and analytical techniques that you can use in your exploration program. However, I'm distilling them down into just 4 different techniques, which act as a summary. You can either apply no digest to your sample. And maybe I should say beforehand, digests means that you employ chemicals to destroy the crystal lattice of your mineral grains, and then free up the elements that you then later analyze in a solution using ICP-MS, for example. That said, you can either apply a digest or no digest, and if you don't apply a digest, that's usually done when you analyze a sample for XRF or portable XRF. You don't need to add any acids here. That's quite useful if you're looking at either bulk commodities such as iron ore or uranium, or if you're in the field with a portable analyzer and quickly and efficiently analyzing the multi-element geochemistry. Next on the slide are what's called aqua regia digest. That's quite a weak acid digest, and it's usually used in weathered terrains. It has the ability to dissolve elemental gold and sulfides. It breaks iron manganese oxides, so usually what you find in the B horizon, and it's able to digest carbonates. However, the largest draw point here is that it's not strong enough to really break down silicates and resistate minerals. Aqua regia digest is commonly used by governmental surveys, mainly because it's cheap and because it is straightforward to do. It provides a multi-element geochemical suite, but if you're interested in more advanced applications such as lithogeochemical mapping and detecting bedrock signatures, this aqua regia digest will not work. I've tried it on a number of data sets, and because the digest is one of the weak ones, it really does not attack the rock-forming minerals. One of the other common digestive techniques is 4-acid digest, and employs 4 different acids, and amongst them is HF, hydrofluoric acid, which is one of the strongest acids available, and that will be beneficial to use on rock samples, and if you're really interested in lithogeochemistry using pathfinder elements. Again, it's a near total digest, and it does not completely dissolve resistate minerals such as cassiterite and wolframite, for example. The strongest digest that you can find is fusion, either using sodium peroxide or lithium borate, and this really leads to a complete digest of the sample that you send to the lab. That's probably the most ideal digest technique that is applicable if you're doing lithogeochemical exploration. So in this list, I have not mentioned these ionic techniques. Ionic techniques such as mobile metal ion or ionic leach, they extract the ions that are bound to the surface of mineral grains. And this is rather a specialized technique. However, it's finding more and more application in the industry nowadays. Now, these techniques lead to the elements being in solution, and you would then run the sample through through analytical instruments such as atomic absorption spectroscopy or ICP, atomic emission, or mass spectroscopy. If you don't use any digests, usually that leads to fused disk S-gray fluorescence analysis. However, the most common technique for mineral exploration nowadays is the ICP, inductively coupled plasma spectroscopy techniques. They really allow you to record 50 to 60 elements if need be, and they are very useful in reconnaissance exploration, lithological and alteration mapping, and mineral systems analysis. If you're looking for elements like gold or PGEs, fire assay is the technique that needs to be employed, as you would not be able to confidently obtain concentration values using these other techniques above. Okay. One aspect I mentioned earlier, which needs to be considered, is quality control. And I show you here a number of charts generated in Excel. It is of great importance that you consider the performance of laboratory equipment, that you consider the effects of contamination or cross-contamination during laboratory analysis. And for that reason, you would insert, as I previously mentioned, standards, blanks, and duplicates into your sample stream. Those two graphs here have been produced quite recently. I tested the performance of the laboratory equipment I was using a certified reference material. In this case, it was Aureas 147. And what you do is you plot the different PXRF, in this case, analytical values against what the certified reference material is certified for. So you will find usually in these certified reference reports mean values and standard deviations. And you can see on the left-hand side here that these analyses have performed and returned values of around -2 standard deviations from the certified value. And that clearly shows a negative bias on the sample or the analysis technique. And that's really important to recognize when you're interpreting your samples, because these values here demonstrate that potassium, in this case, is underreporting and should actually be corrected. And in order to correct or provide these correction factors for your PXRF, you can plot a number of these certified reference materials on an XY graph, and you calculate the linear regression line through the origin. And that M value here in this equation is giving you the correction factor for that you can apply to your raw portable XRF data. Moving on to a few case studies here, and showing you what source samples can actually do for you. This is a project I recently worked on in South America. We were looking with a junior company to delineate porphyrin epithermal deposits in the Salta province of Argentina. And A multi-element suite was obtained from a number of samples across a caldera. On this Landsat image, you can clearly see the alteration halo of that caldera, which forms these green to light blue hues. Now, those were initially sampled during an orientation survey and analyzed for a Pathfinder element suite. Now, instead of plotting just the absolute values and the in the common 95th percentile or higher distribution of the univariate values, I employed what's called principal component analysis. And that is a real powerful tool to delineate trends and metal associations in a multi-element geochemical data set. So you can see on these two graphs on the left-hand side, the top one is plotting principal component 1 against principal component 2. And you can clearly see that there are a number of trends in the data. So the trend to the left-hand side consists of a potassium, rubidium, and niobium suite. And this usually is a very clear indicator for a felsic intermediate to fractionated, intermediate to felsic fractionated trend, whilst on the right-hand side with positive PC1 loadings, we can observe an element association of lead, copper, and arsenic, molybdenum, and bismuth as well. Now, if such trends are being delineated in principal component analysis and then plotted on top of a geological map or a Landsat image, you will see that here we have these trends actually following certain areas throughout this caldera. So the center of the caldera forms this copper, arsenic, and lead association, whilst the intermediate to felsic rocks are found on the boundaries of that caldera. Now that is potentially good news if you're looking into these epithermal deposits, as you have clearly this metal suite of interest, these pathfinders delineated quite effectively. So my opinion is that instead of just using probability plots and univariate analysis tools, it's much more useful to look at multivariate analysis in order to delineate meaningful trends and generate exploration targets in that way. The next example is from the Central African Copper Belt, where quite a lot of soil samples have been taken in an area. You can see on the left-hand side the distribution of soil samples. And on the right-hand side, I've generated a pseudo-radiometric image. It's a ternary image comprising potassium, thorium, and uranium. Now, that usually gets by using airborne geophysics if you carry out magnetic and radiometric surveys. But you can, of course, also try to plot such a map using soil geochemistry. And that worked particularly well in this copper belt setting here, where we have a number of important target lithologies and formations present that companies are exploring for in that part of the world. It allows us to determine different geochemical trends, and by applying lithogeochemical mapping in soils, we get these typical trace element signatures that are characteristic for underlying bedrock geology. Okay, so in this particular case, it was important to delineate gabbro intrusions. As in the copper belt, gabbro intrusions usually represent false anomalies and are not, the copper mineralization around these gabbros is usually not related to any strata-bound sedimentary hosted copper occurrences. Now, knowing these that these gabbros are present and mapping them using titanium, zircon, and thorium trace elements, that will really be very powerful to delineate such occurrences before drill rigs move in and drill these false anomalies. Okay, that leads us to the last Q&A session. I have a number of questions appearing on my screen. A question was, how can we define the threshold for an anomaly based on the acquired geochemical data? That is usually done using probability plots. If you produce a cumulative frequency curve and you inspect where the data distribution starts to break and form individual geochemical populations, that is the tool to usually very quickly look into what is background and what is anomalous. Of course, there are also other multivariate tools available to determine the thresholds, but a quick and easy fix would be using probability plots. Another question was soil geochemical techniques, would they be the same for glacial sediments? I assume you're referring to glacial tills. The techniques are generally the same. However, you need to consider a number of aspects here which are particular to glacial sediments, such as transportation distance, that you can determine by investigating the quaternary geology in striations. You also need to consider what soil horizon to target. As I mentioned earlier, if you want to avoid secondary dispersion, you probably have to sample quite close to the bedrock, which in some cases mean drilling down up to 10-15 meters to reach bedrock. You could also consider looking into these ionic techniques. However, it should be that the techniques that to obtain a soil sample are quite common, yes. Let me look for a few other questions here. In the desert, which soil sample depth is recommendable for taking samples? Well, a geochemist once told me, don't waste your efforts on collecting soil samples in the desert, just drill. That is probably the shortest answer to that. However, of course, desert soils might take different formats. So in some parts of the world, you have carbonate soils, and others you have sandy soils which have been transported by wind. So really, I cannot give a definitive answer for that. You should do an orientation study and determine has secondary dispersion taken place, and does any soil horizon in a desert soil give you an appropriate signal. Another question was, how can we determine what are the best sieve sizes for the minerals of interest? Are there reliable online resources for this info? Well, again, I need to refer you to carrying out an orientation study and to subsample the soil profile at the location you're exploring, just to see which is the best, not only the best horizon, but also the best sieve size that you can use. And I think there's one last question here. Which elements would you follow up in soils to find a porphyry deposit? And which ones do you use for orogenic gold? So in the traditional techniques for porphyry copper exploration, of course, used to be analyzed for copper, lead, and the base metals, and of course, gold. However, in porphyry deposits, what we usually see on surface are the alteration halos that form quite widespread around these porphyry stocks. So you need to investigate which trace elements are located and are found in these porphyry alteration halos, and that usually is are elements like bismuth, thallium, tellurium. I need to add here that these trace elements are often in quite a low abundance, often below the actual detection limits of many different techniques, especially XRF. So if you're looking for these, for example, bismuth in a porphyry copper deposit, you need to choose an analytical technique which has very low detection limits. And for that, you can probably only use ICP-MS and one of the 4-acid digest packages that are available. Okay, for orogenic gold, it's not too dissimilar. You would, of course, analyze for gold, for arsenic, tellurium, bismuth, and you then also need to determine what kind of orogenic gold signature is it. What I just gave you was the typical orogenic gold signature. However, in some greenstone belts, such as the ones in Finland that I've been working on for some time, you have what's called an atypical signature. These gold deposits are intimately related with graphitic schists, and those graphitic schists form an interesting redox boundary that attract all sorts of other metals, such as nickel, copper, and even uranium. So if you're looking for such an atypical signature, you would, of course, follow up these atypical signatures as well. Very good. Thank you very much for putting forward such interesting questions. I hope I could have answered those in detail, satisfactory detail. I think that brings us to the end of this webinar. And just moving on to the next slide here. I wanted to inform you about the topic for the webinar in December. We discuss even more technical aspects of mineral exploration and gradually move on from target generation to target testing. The topic for the next webinar will be drilling techniques. And I would like to give you an overview of what drilling techniques are usually employed in mining and mineral exploration. We're going to learn about the importance of choosing the right the right drilling technique. And I will also talk about the on-site responsibilities of geologists and technicians. Because of course, if a lot of money is spent on drilling campaigns, we need to ensure that the maximum quality of data and of drill material is extracted from the ground. With that, I hope you enjoyed this webinar, and I hand over to Deanne to say a few words. Thank you very much, and I hope to see you next time.
Great, thanks, Benedikt. And if anybody has additional questions, here's Benedikt's contact information. And as he mentioned, our next webinar will be December 11th on the drilling techniques to maximize exploration success. And I would like to ask everyone who's on this webinar to complete the survey that you'll see at the end, just to give us feedback so that we know what you liked and what you didn't like, and we can go from there. And I want to thank everybody for your time and hope to see you next month.